Dear organizers, dear Fernando, thank you very much for the invitation to the 11th International Symposium 2021. It's a great pleasure and also great honor for me to contribute to this conference. Now, I would have loved to come to Cuba in person, but this is not possible, obviously. So I hope very much that in the near future we can see again in person. So today I'm talking about the revised SI, International System of Units, for innovation, science, and the second quantum revolution. And allow me to start with a little historic excursion. So this is PDB, founded in 1887 as the first metrology institute worldwide. The first president, this was Hermann von Helmholtz, one of the really great persons in science of his time. And on the other side, on the industry side, we had Werner von Siemens, who had just founded a large company which was growing and growing. And finally, as a third contribution, we always had verification in the person of Wilhelm Förster. So this is how we worked all over more than 130 years now. And in our scientific advisory committee, we had 14 Nobel Prize winners, and still 3 of them we have actually today. Now, and this brings me now a little bit closer to the topic of my talk. This area is a birthplace of quantum mechanics. In this building, there were experiments done by Otto Lummer and his group in the PTR on black body radiation, and they got results which they could not explain in the present theory. So they called Max Planck, and Max Planck was in the curatorium of the Reichsanstalt, and he said, in an act of despair, he had to quantize the radiation field. And this is his famous equation, and you see here is a Planck constant H, which he had to introduce. Now, at the end of his talk, when he was, of his paper, where he was explaining this quantization and the radiation law, he was reasoning about units. And this is in German, and I translate it for you. He was saying, with the help of fundamental constants, we have the possibility of establishing units of length, time, mass, and temperature, which necessarily retain the validity for all times and civilizations, even extraterrestrial and non-human. And this was a very visionary definition of units, and exactly this is what we have done in the revised International System of Units. So in this inner circle, we have fundamental constants, many of them fundamental constants of nature, where we fix the numerical values, and by applying the laws of physics, we can then realize the units. And I'm going to show you, at some cases, how this works. Altogether, this is a consistent and a coherent set, and it is based on our present understanding of nature. Now, this was then brought into being on the 26th General Conference for Weights and Measures in 2018 in Versailles. We had 2 Nobel Prize winners giving lectures. So this was a very historic and actually also a very emotional event, because all of the nations in the meter conventions, close to 60, were agreeing to the revised International System of Units. So this was a very brief introduction into the SI. In the second part of my talk, I will explain it in a little bit more detail, but also show you examples where the revised SI contributes to innovation and science. In the third part, I show you that the revised SI underpins the so-called second quantum revolution. And finally, if I have some time left over, I will talk a little bit about the future of time. The revised SI for innovation and science. Let me start with time and explain you again how this unit definition works. So here is the definition of the second, and this is based on a transition on a frequency in a specific atom, namely the cesium-133 atom. And there's a little pendulum in this atom, and we define the second to be exactly 9,192,631,770 oscillations of this little pendulum in the atom. So this is how you define a unit, by fixing the numerical value of a constant of nature. And this is what we exactly do with all the other constants, as I'm going to show to you, and units. Now, Dissemination of time and frequency. So presently at PDB, we have the highest reliability. We have a very small uncertainty in the order of 2 times 10 to the minus 16. And this is very important for innovation. This is the most accurate realization worldwide. And therefore, we contribute to the world time presently by about 50%. And this has a lot of impact for innovation because we are responsible for the coordinated time for the Galileo satellites and also for a satellite mission where atomic clocks are brought in space, ACES. Now, the next generation of clocks would be even more precise. And in order to do so, we need a pendulum which is much, much faster, 500,000 times faster. And this means if we go into an atom or an ion, these are so-called optical transitions. And we use ytterbium plus ions, an octopole transition at 467 nanometers. And with these kind of clocks, with a single ion trapped and cooled, we can achieve a systematic uncertainty in the order of 3 times 10 to the minus 18, which is among 5 other national metrology institutes about the world record. Now, this is 2 orders of magnitude better than the present SI second, and it's very much based on innovation, namely on the so-called frequency comp technology, which was invented, among others, by Theodor Hensch, who got the Nobel Prize, and who is in our curatorium of the PDB. And this helps us to bring these very, very fast frequencies down to something, to radio frequencies, which you can easily measure. Now, these clocks have to be connected in order to generate a world time. How to do that? Because usual radio frequency transmission doesn't work anymore. It's not precise enough. So what we have invented at PDB together with Paris is that so-called optical fiber transmission. So we give this frequency through an optical fiber, and we can show by a kind of an interferometric approach that we can reach the relative uncertainty in the order of 10 to the minus 20 frequency transmission from PDB to Paris and even to Great Britain, to London. And recently we have compared 2 optical clocks on the level of 10 to the minus 17, which is about a factor of 10 better than the present SI second, and which is world record. In the future, however, we have to bridge continents, and this only goes through satellites. And so our colleagues at NIST, Yunye, have demonstrated that they could transfer such frequency via a laser with a relative uncertainty in the order of 10 to the minus 18. And as our Chinese colleagues demonstrated for entangled photons, this then has to go through satellites to come from one continent to the other. In Europe, we are planning a fiber network for these kind of high precision frequency and time transmission through these fibers. This can also be used for quantum cryptography and for ultra-broadband information transmission. So a lot of innovation connected with this kind of realization of the second. So another step forward is that we have generated, or we have built a next generation portable clock based on these optical clocks. And this should replace the maser, the hydrogen maser, which usually has an uncertainty in the order of 10 to the minus 15, but is not very stable. But such an optical clock is usually something like that. It's a very complicated machine where you can reach a relative uncertainty of 10 to the minus 18 in the laboratory. Now we have built a consortium with other research institutions, but with many industry companies as well. And we have realized a push-button machine in such a rack which can be bought essentially with a relative uncertainty smaller than 10 to the minus 16 and a very good stability. And this is important for the future of data network synchronization and geoid survey. So these were some examples from time, and this brings me now to mass. In order to realize the kilogram in the new SI, we need 3 fundamental constants. Planck constants, the speed of light, and this transition in the cesium atom for the second. Now, we realize the kilogram at PDB via the so-called Avogadro silicon route in the Avogadro collaboration, which is a large collaboration of different NMIs. And what we do is we count the number of atoms in a crystal sphere of enriched silicon-28. Now we have the number of atoms, and now we need a mass scale. And the mass scale is actually given by quantum mechanics. Just by, if you solve the Schrödinger equation for the hydrogen atom, you will see that the mass of the electron is given by 2 times the Planck constants times the Rydberg constant divided by the speed of light and the fine structure constant squared. So 2 of them, the speed of light and the Planck constants, are fixed, numerically fixed, and the 2 others we can measure with very high precision. So we get a mass scale by quantum mechanics, and now by counting the atom and transmitting the electron mass or relating the electron mass to the mass of a silicon atom, which can easily be done, we can realize the kilogram in the new world. As I said, a large collaboration, very successful collaboration, which brings us really to the top high-tech technologies, and we need a lot of innovation. So in order to realize the kilogram on this level, we need the most advanced surface technologies, surface analysis technologies like XRF and XPS. We need ultra-precise lattice constant measurements on the level of 10⁻⁹ from our colleagues from Italy. We need to control impurities in this silicon on the order of smaller than 10⁻⁹. We need to control lattice imperfection on the same level, and we need to measure the isotope contribution actually also on the level of 10⁻⁹, which by itself is the most precise measurement that has ever been done in chemistry. Finally, we need to measure the volume of the sphere. And this brings us to dimensional measurement at its absolute limits. So the sphere is about 9 centimeters in diameter, and we make it completely round, and the deviation in the sphere radius is in the order of 10-16 nanometers peak to valley. On the right-hand side, you see a kind of a topography on the nanometer scale, and this is the roundest object in the world. So a lot of innovation and high tech is needed to realize the kilogram. But now we have new possibilities. So far, we could realize the kilogram only at one point, namely at 1 kilogram. But now, this little sphere can be even shrinked in size, even down to nanospheres, and then we can realize in a primary way, we can realize the kilogram over a large part of the scale. And that you can see here on this scale, where we plot the relative uncertainty, dissemination uncertainty of the kilogram by PdB over essentially the entire scale. The red curve is what we have today. So we have very low uncertainty at 1 kilogram, as you can see here. And then it's getting worse because you have to subdivide it to smaller masses. But now, this is a blue curve. We could directly count the atoms in a nanocrystal. And then at below 1 microgram, we get, or below 1 milligram actually, we get much, much better and in the realization orders of magnitude, and this would be actually the blue curve. Now we can even go to atomic masses. For the very first time, atomic masses can be realized in the SI by essentially 2 experiments, and one I would like to explain you, and this brings us down to masses of 10⁻27 kilogram. And one of these experiments works like follows. There's a single photon and a single atom, and this single photon is absorbed by this atom. So at the end of the day, the photon momentum has to equal the atom momentum. We know the photon momentum. This is the Planck constant times the frequency times k, and then this has to be equal the momentum of the atom, which is the mass of the atom, and the velocity change of the atom. And the velocity change of the atom we can measure with high accuracy via interferomic technologies. Now then you see the mass is given by the Planck constant and some measured quantities. So for the very first time we have a primary realization of atomic masses. And even in this area down to 1 milligram in the future, we think at PdB and at other places we will become better by using the so-called Kibble balance. The Kibble balance is the second realization of the kilogram for macroscopic masses in the new SI. And what we are aiming at realizing the kilogram from 1 kilogram down to 1 milligram. This is a green bar with a relative uncertainty in the order of 10 to the minus 7. And that would then finally bring us to much more precise dissemination of the kilogram over a large part of the relevant kilogram scale. And this Kibble balance actually is a large collaboration as well, and will be a primary balance which can be used by calibration laboratories actually. Let me continue with the ampere. And here we fix the electron charge. This is conceptually now very simple. If you have single electrons, these little dots, which you get into a potential and throw it out again by switching the potential, then the current by these single electrons is just given by the number of electrons in this little dot times the electron charge times the frequency where you switch these potentials. So conceptually very simple. Technologically, this is a huge challenge actually, but we can do that at PDB, for instance. So the device which you see is a so-called nanodot. You see these little stripes. These are the potentials which we switch. Then an electron hops to one of these platforms, and the platform is a detector. And on this detector, we see the signal of a single electron. Then comes another pump, another detector, another pump, just to make sure that we always pump one electron. And finally, we can realize very small currents in the order of 10 to the minus 7, which is world record actually. And this kind of single electron pumps finally has a lot of future applications. So obviously, this is a kind of shot noise-free electronic because you control the electrons. This is the basis, or could be the basis, for quantum spin electronics. You could implement also photonic technologies if this electron is in excited states and radiatively decays. And it is a basis for quantum information readout. So at PDB, we have a project where we work towards reading out quantum computers by these kind of electronics. Now, if you would like to amplify this current, this very low currents, to something which you can easily measure, then you need a current amplifier. And we have developed, and this is a classical instrument now, an ultra-low noise current amplifier at PDB, which by itself helps us a lot to improve our dissemination. And here you see our dissemination relative uncertainties for the ampere now again over the entire scale. And you see that below 10 micron amperes is getting worse, but now this ultra low noise current amplifier sets in, and you see that we can improve the situation by about 1.45 orders of magnitude, and at even smaller currents. Now these single electron pumps set in. And we have measured 2 points, one at 100 picoamperes in the order of 2 times 10 to the minus 7, and at an atto ampere also on the order of 10 to the minus 7. And what you see here is that finally, with all of these measures, we can now improve our dissemination uncertainty quite a lot. Now, this has a lot of practical applications, which these ultra-low current amplifiers are already in use in ionization chambers where you have to measure very small currents. And the red line here is a zero line, and plus minus is the uncertainty which these ionization chambers work in the moment. With this new device, we can improve significantly, as you can say, the uncertainty budget. So there's a lot of innovation also due to the fact that we have developed these kind of things which we need for the realization of the new SI. And there's a lot of other possibilities now in the revised SI, because you can directly realize the ohm by the ratio of the electron charge and the Planck constant through the von Klitzing effect. And you can directly realize also the volt, again, the same constants, by the Josephson effect. And here we have a lot of possibilities for innovation, in particular also for the ohm. Here at PDB, we work on quantum Hall resistance in graphene. So the goal is that we operate these devices at smaller magnetic field, and this is then better for commercial devices because it's less expensive. So we were able to produce epitaxial graphene on SiC established at PDB. Here are these kind of sheets where we have nearly very equally distributed single layer distributions. And finally, we could demonstrate excellent DC and AC quantum Hall effect down to 1 Tesla. Usually you have something like 6. And this has to be optimized now and in order to get a stable and robust carrier concentration. But the door is wide open also for topological insulators for innovation here. Now let me very briefly come to the Kelvin. As you see from the equation here, if you have an ensemble of particles, you can relate their energy with their temperature via the Boltzmann constant. This is for 1 degree of freedom now. And from that now, you can build a commercial thermometer, a primary thermometer, for instance, by noise thermometry. This was pioneered by our colleagues from NIST and from China, but now we try at PDB to build a commercial device. What do? You have a resistor at a certain temperature, and this is producing noise, obviously, quantum noise, and electronic noise. This depends on the temperature. So at the same time, we make synthetic quantum noise by Josephson contacts, and by comparing these two, we get to this equation which you see. And as you can see, this is a possibility to realize the temperature by fixing the numerical value of the Boltzmann constant. And this project is going on at PDB, and we hope in a year or two that we can come to a commercial primary thermometer, which covers quite a large area of over the scale. Now, and this were some examples on innovation and science, and this brings me now to the so-called second quantum revolution, which is also connected to the fact that we now can control individual quantum systems. And here we have a quantum technology program from the government in Germany, and PDB is involved in that. So we are building up a quantum technology center in Berlin. This is the upper right picture, where you see a completely new building, and another one is just being built at Brunswick. And what we do there is we look for quantum sensors for small magnetic fields. These are squids, essentially. We do electric quantum metrology, as I explained to you before. We do innovation for time and frequency. And finally, also, we are involved in quantum communication and quantum computing simulations. And we are also building actually a quantum computer, and this is shown here. How do you do that? This is based on our technology, which was developed for optical clocks. And these are small chips where we can move individual atoms, cold atoms, and each of the ions is 1 qubit, so we can move them around, and by that we can, for instance, realize then a gate with 2 qubits. We can also realize a gate with 1 qubit, and then we can finally also read it out. So we have all elements of a computer, storage, computer operation, and readout finally by a laser. And the interesting thing is that all of that can be really scaled. So very recently we have shown that we can realize a 2 qubit gate with a relatively small error rate of 10 to the minus few times 10 to the minus 3. We can improve that, I think, by an order of magnitude. And all of that is on little chips which can be scaled such that we can build in the future a 20 qubit or even a 50 qubit error-corrected computer. And for that, we have recently got a lot of funding, 25 million euro, and we founded Quantum Valley Lower Saxony, and here are all the partners, and the goal is to have within 5 years a 50 qubit quantum computer realized. And this then finally brings me to my last part about the future of time. And this brings me actually to science. How will we contribute with a revised SI, or even a step further with the next generation of clocks, how we can contribute to science? Now, in this picture, you see the relative uncertainty over the years achieved in the realization of the SI second, which is cesium-based, as you can see here, since 1967. And since 1967, where we achieved the relative accuracy of 10⁻12, until now, a few times 10⁻16, we have improved things, or the realization of the time of the second, by 4 orders of magnitude without changing the definition. And this is one of the beautiful merits of the revised SI, that if technology proceeds, you can go better and better. Nevertheless, there's a limit because this pendulum is not fast enough. And as I said, now we have so-called optical pendula, which are much faster. And as you can see, many laboratories in the world now have reached, as I said before, a level of 10⁻18 relative uncertainty. So 2 orders of magnitude better than the SI second. And there is no limit to be seen in order to further increase that. So I recently heard a talk by Yun Ye from NEST, and he was very much convinced that in his lifetime at least, he will reach something like 10⁻21. And this opens huge potential for sensing, but also for science. One of them, and this is already now with 10⁻18, very interesting, is so-called relativistic geodesy. As you all know from Einstein's general gravitational theory, clocks tick differently at different places in the Earth's gravitational field. So if you take a clock in the Earth and lift it by 1 centimeter, you will change its frequency roughly by 10⁻18. So in the moment with our clocks being accurate on the level of 10⁻18, we are sensitive to 1 centimeter in the Earth's gravitational field. And for that, now we built a transportable optical clock where we can drive around and measure the frequency, and by that get information about the geoid on a level which was not possible before. If you use traditional methods, the accuracy, the relative accuracy, the order of 20 centimeters, and here we aim at 1 centimeter in the future. And you can easily think, if we go to 10⁻21, these sensors would be accurate on some micrometers in the Earth's gravitational potential, which would be a revolution by itself. With these clocks, we can also search for dark matter, actually, because they would tick differently if dark matter would pass through the Earth. And we had a first beautiful experiment on that. Unfortunately, I have no time to show you. You can look for Lorentz invariants. And again, we had a beautiful experiment on that, where we looked for differently oriented atomic clocks where the orientation of the excited state was differently. And so by the variation and the turning of the Earth, we could look for Lorentz invariants of electrons, and we got the best value ever achieved. And you can also look for gravitational wave detection in the future, but this is a vision. We haven't done that. If you have 2 atomic clocks on 2 satellites, if a gravitational wave arrives, the time-space continuum will change, and you will see that in the clocks. And finally, we can ask the question, are the constants which we have defined in our system, which we need for the units, to realize the units, are they really constant? And this is a very basic, fundamental physics question. We are looking now on alpha, on the fine structure constants, where the electron charge, the Planck constant, and the speed of light are as components in there. And this fine structure constant actually governs the transition frequency in atoms. So the transition between A and B, and both levels react a little bit different on an alpha change. So if alpha would change, you would see that this frequency would change. And this is what we investigate in our interbium clocks, actually. And we have 2 transitions with different sensitivities on alpha, as you could see, so they change differently. And by comparing that, we could then finally show that in the moment we could set the best limit for potential alpha variation, namely saying that alpha is not changing by more than 1 times 10⁻18 per year. And if you compare this transition then with a cesium clock, then you get actually also again some information about another very fundamental quantity, namely the electron mass to the proton mass. And here we could set a limit of a few times 10⁻18 18, again, per year maximum change of this ratio. So we are very sure, actually, as you can see, that our constants are really stable on the level of 10 to minus 18, but it would be very interesting to really see deviations, and these are predicted in grand unified theories, and we have ideas how to do better, but I have no time, unfortunately, to explain you to that. Now, this is the end of my talk. Thank you very much for your attention. So I hope that I have shown you that the revised SI allows us a lot of innovations. So it's completely open to innovation. It's open to new technologies. So the definition of the units is not anymore any limitation for the dissemination accuracy of the units. So we can do a lot of science and we can massively support the second quantum revolution. Thank you very much for your attention.